Hello, everybody. Welcome to the second week of this online numerical and algebra seminars. I hope you have enjoyed the first seminar, and it was very well attended, and we are very happy that the initiative was so well taken. And today we are very happy to have another prestigious speaker here. And in particular, I'm very happy to introduce Michele Benzi from the Scuola Normale Superiore in Pisa, Italy. And he will talk about non-local dynamics on networks via fractional graph Laplacians, both theory and numerical methods. Please, Michele.
Well, thank you, Valeria. So I would like to start by, first of all, thank the organizers for the invitation and for inviting me, but also for creating this series of seminars. I think it's very important to maintain a certain level of scientific activity even during these extraordinary times. So I would like to talk about recent joint work I did together with Daniele Bertaccini from the University of Rome, Tor Vergata, Fabio Durastante from the Istituto per le Applicazioni del Calcolo of the CNR, and with my student Igor Simune, Scuola Normale Superiore. And especially thankful for Igor also for help with the slides. The paper is available in the archive, and it was accepted, in fact, yesterday in Journal of Complex Networks. So all the details will be there. And we've got some funding for this project from INDAM and from the University of Rome, Tor Vergata. So the outline of my talk, there will be an introduction first with some definitions and notations. So let's move on. So the notation I will use is fairly standard. So we will work on graphs. Generally, they could be directed or undirected. So graph is just a pair of sets, a set of nodes, V, with n elements, and a set of edges, which are pairs of nodes connected by some kind of relation. The graph G is undirected if we don't distinguish between a connection between I and J and between J and I. Otherwise, if we need to distinguish the directionality of the connection, we talk about a directed graph, or for short, a digraph. Simple examples of undirected graphs would include, for instance, transportation networks, such as a road network, if we don't include one-way roads, of course, or the Facebook network, where relationships are friendship relationships. On the other hand, if we look at the web with hyperlinks going from one web page to another page, or online social networks like Twitter, where the follow relation is directional, then we're looking at directed graphs, of course. A great deal of information on the structure of graphs and also on the behavior of dynamic phenomena taking place on graphs and networks can be gained by looking at certain matrices associated to the graph, and in particular the adjacency matrix and the graph Laplacian. So if the graph is unweighted, and in this talk I will limit myself to unweighted graphs, though a lot of what I'm going to say can be generalized to weighted graphs. So for an unweighted graph, the adjacency matrix is just a 0, 1 matrix where we put a 1 in position ij if there is a connection from I to j, and 0 otherwise. We also define the degree of a node, more precisely the out degree, as the number of edges starting from node I. So if the graph is undirected, of course, the matrix A will be symmetric, and we just talk about the degree of a node. If the graph is directed, then in general, the adjacency matrix will be non-symmetric, and we focus here on the out degree, so count the number of edges. Of course, we could also consider the in degree, which is the number of incoming edges to a node, but here we our focus will be on the out degree. And if we denote by this bold-faced one, the vector of all ones, then the vector of degrees, of out degrees in particular, is just the row sums of A. So it can be computed by the matrix vector product of A with the vector of all ones. We can also define the degree matrix, which is this matrix D, consisting with the out degrees. And then we can define the graph Laplacian of the matrix, of the graph, sorry, as the difference between the degree matrix and the adjacency matrix. So there are several things to be said here. I already said A, but also L will be symmetric if and only if the graph is undirected. Again, I want to emphasize that in the directed case, this matrix D will be the matrix of out degrees. It's called the graph Laplacian because, at least in the symmetric case, it really corresponds to a sort of a discretized Laplacian operator with Neumann conditions. So in this talk, I will focus primarily on the graph Laplacian. It has several important properties. By construction, the row sums are 0. This implies, of course, that the graph Laplacian is a singular matrix. In fact, it is a singular M matrix. The off diagonals are, of course, non-positive. And moreover, the Laplacian can be written as the difference of a scalar multiple of the identity, S times I, minus a non-negative matrix B, the spectral radius of which is equal to S. So this is one of the definitions of a singular M matrix. It's well known that in general for a singular M matrix that the eigenvalues of L all have non-negative real parts. And this is very important for what will follow. The index of L is 1. By this we mean that the eigenvalue 0 is a semi-simple or non-defective eigenvalue of L. The index is defined as the size of the largest Jordan block associated to the 0 eigenvalue. So the index will be 0 for a non-singular matrix. For a singular M matrix, which comes from the Laplacian, for the Laplacian in particular of a graph, it can be shown that the eigenvalue 0 will always be semi-simple. Moreover, if the graph is undirected, then the multiplicity of the eigenvalue 0 gives the number of connected components of the graph. In the directed case, this is not true in general. However, it is true that if the graph is strongly connected, which means that every node can be reached from any other node by following a directed path on the graph, then the eigenvalue 0 has multiplicity 1. And in most of what I said, I will be focused primarily on strongly connected graphs. So these last 3 bullets are consequences of the Perron-Frobenius theorem. They're fairly straightforward consequences. And as you will see, they will be necessary in order to define certain matrix functions of L. Okay, so in this talk, we'll discuss different kinds of dynamics on graphs. In particular, we're looking at diffusion type dynamics and both continuous and discrete random walks. As we will see, this is motivated by certain applications. So in analogy with the continuous heat equation, diffusion equation, one can study diffusion on a network or graph. And this is best written in terms of a probability distribution that evolves on the network. So if we start from an initial vector, which is a non-negative vector, the entries of which all add up to 1. If you wish, you can take any vector from the unit basis, which will mean that initially the state of the system is given, and the system somehow the substance that is diffusing, or the heat, is concentrated on one node and 0 everywhere else. And then we let this probability distribution evolve according to this system of ordinary differential equations. Now, this may look a little bit strange if you're not used to probability vectors. Typically, probability vectors are written as row vectors. So my probability vector here, ut of transpose, acts, so that the matrix L acts on the right of this probability vector. If you don't like this, you can just transpose everything, and then we would have something more standard looking, but then we would have L transpose here. Of course, in the case where the graph is undirected, then L is symmetric, and this would just be first derivative of u with respect to time equal minus L times u. But in general, since we want this probability vector to remain a probability vector for all times, we need to write the equation in this form. So this is a quantity, if you like, that diffuses on a graph or network. Oops, I went the wrong way. So another type of process that is important, more closely related to Markov process, is to normalize the graph Laplacian. So here I'm assuming that the graph is strongly connected, so every node has out degree at least one. So this diagonal matrix D is invertible. So if I normalize L, so I divide each row of L by the corresponding entry of the diagonal matrix D of out degrees, I obtained the so-called normalized graph Laplacian. Normalized graph Laplacian will be written by L script, calligraphic L. And now I can still continue to consider the diffusion type equation given by the system of ODEs with these initial conditions. Again, these are continuous time Markov process. And in particular, this vector x of t is a probability vector for all t. I can also look at a discrete random walk instead of a continuous time random walk, observing that if I subtract this matrix L from the identity, I'm left with a row stochastic matrix. So this will be the transition matrix of a Markov chain, of a finite state discrete time Markov chain. And the evolution of the Markov chain is simply given by this fixed point type of iteration here. So all these dynamics, when they're applied to sparse graphs, and we'll be mostly interested in sparse networks, are dynamics of a local nature. In particular, if we think of the random walk, the discrete random walk, the particle, if you like, or the individual, the agent that is evolving, that is moving on the graph, is only allowed to make a transition from one node to a neighboring node. In particular, if it's a directed graph, it has to follow the direction of the edges. It cannot suddenly jump from one node to another, which is far away. So you can only move from a node to a neighboring node. Similarly, the diffusion, the time continuous process is sort of localized, as we will see, because diffusion takes place over time according to a process that is essentially localized, as I will explain shortly. So recently, there's been a great deal of interest in modeling phenomena that are non-local in nature. By which I mean that the agent that is moving on the network, the random walker, if you want, is allowed occasionally to perform transitions to faraway nodes. So long distance moves or jumps. They're also called flights. There are many phenomena that require this type of processes for modeling. Human mobility is one of them. And of course, this is painfully actual, timely, because in fact, there are epidemic spread model that most epidemic spread models that are based on networks have to incorporate the fact that humans, for instance, or animals or whoever it is who's spreading the disease, tend to stay put in their neighborhood for most of the time, but occasionally perform jumps to faraway locations. For instance, they take a flight from one country to another or from one state to another. So this is only one application. Also animals with their periodic migrations tend to follow a pattern of this kind. even cash, like dollar bills, for instance, follow a dynamic where they tend to remain in one place, in an area for some time, and then occasionally they disappear, they reappear in faraway places. So there are many situations that call for non-local type of diffusion or non-local random walks. One paper that got our interest was this paper here by Riascos and Mateos in Physical Review E, which was one of the first to propose the use of fractional power of the graph Laplacian to model this kind of phenomenon. So the idea in Riascos and Mateos paper is very simply to take fractional roots of the Laplacian. In their papers, they focused on the undirected networks. So the graph Laplacian is a symmetric positive semi-definite matrix. It can be diagonalized by an orthogonal matrix. And so if we define as lambda, capital lambda, the matrix of eigenvalues, then the alphath power of L is simply obtained by taking Q times the alphath power of lambda times Q transpose. Here alpha is a real number between 0 and 1. The matrix L of alpha, of course, is just a diagonal matrix that has the alpha powers of the eigenvalues on the main diagonal. So this is just a standard matrix function for a diagonalizable, in fact, a symmetric matrix. So this does not present any difficulty. If we want to extend this to the unsymmetric Laplacian, so to directed graphs, which is one of the things we did, we need to be a little bit more careful. We have to use the Jordan form, and we have to make sure that indeed these fractional powers are defined. So we write the Jordan form of L as a matrix J, which is a direct sum of diagonal Jordan matrices corresponding to distinct eigenvalues. There can be several Jordan blocks, of course, for each eigenvalue. Then we define the alpha power of L through the similarity transformation given by Z, just by taking the alpha power of J. So the alpha power of J is the sum, direct sum of the Jordan matrices to the alpha power. So we have to define what it is, the alpha power of a Jordan block. So basically we open Nick Hyam's book, for instance, and we go and look at the definition of a function of a matrix to the Jordan form. And we find that for an eigenvalue lambda, the Jordan block corresponding to that lambda to the power alpha is given by this triangular Toeplitz matrix that contains the binomial coefficients and the powers of lambda. And you see immediately that if alpha is less than 1, this block is defined only for lambda not equal to 0, because for lambda equal to 0, this is not defined already. So all the entries above the main diagonal would not be defined for lambda equals 0. So this is important because it means that in order for the alpha power to be defined, we need the 0 eigenvalue to correspond to linear elementary divisors, or if you like, to 1-by-1 Jordan blocks. So we cannot have Jordan blocks of size 2 or larger associated with the 0 eigenvalue. But this is precisely what happens with the out-degree Laplacian of a directed graph. So, the good news is, of course, the matrix L to the power alpha is defined in fact, for any singular M matrix of index 1, and therefore in particular for the graph Laplacian. Not only that, but we can always choose a determination of the alpha power. This is, of course, a multi-valued function, but we can always choose one that corresponds to a singular, to an M matrix. And of course, it's necessarily a singular M matrix of index 1. Now, this brings to an interesting observation, a very simple but interesting observation. The fractional Laplacian is still an M matrix, singular M matrix. It still has row sums equal to 0. So it is itself the Laplacian of a graph, of a network. In general, this is not a sparse matrix. In fact, if the graph is strongly connected, the matrix L is irreducible, then the matrix will be full. So it is going to be the Laplacian of a weighted complete graph. So every node is going to be connected to every other node. And the strength of the connection, the weights, are precisely the entries of this matrix L to the power alpha. So when we define, so we can use this, then, this observation to define the normalized fractional graph Laplacian. So if we take out the diagonal part of L to the alpha, it's a positive diagonal matrix, we invert it, we scale L to the alpha on the left by this, we obtain a normalized fractional graph Laplacian, and if we subtract that from the identity, we obtain a stochastic matrix. So we still have the possibility to define not only fractional diffusion processes, but also fractional random walks and fractional, both continuous in time and discrete in time. The difference is now we have dense matrices, even if the graph originally was very sparse, but that's precisely what we want, because we want to be able to define a non-local dynamics, where there is a positive probability of transitioning from any node to any other node in the network. So we do that, we use these matrices to define the fractional dynamics. And so for fractional diffusion, we just write exactly the same system of ODEs, except that now we will use L to the power alpha instead of L. And of course, we can solve this system of ODEs through the matrix exponential. The solution will be given by evolving the initial probability distribution in time by this matrix exponential, e to the minus t times L to the power alpha. Similarly, we can use the normalized fractional Laplacian to define a continuous random walk, continuous time random walk. And similarly, the solution here is going to be given by a matrix exponential. And finally, we can also introduce the discrete time random walk, which is the same Markov chain type of process that we had earlier, except that now we use the matrix P to the alpha, which is a row stochastic matrix obtained from the normalized Laplace. Okay, let me pause for a moment, and maybe I'll give people time to write if they have any questions.
Okay, can you hear me? There's one question. Can this be applied to the maximum clique problem, which is by Mohamed Al-Kahanti? That's the only question so far.
I don't know. Maybe. It's really not what we are aiming at here. Here we're really not so much looking at structure of the graph, but as studying the dynamics of processes taking place on the graph. So our focus is not so much on structural questions like that.
Mm-hmm. And then the second question, if the Laplacian L is a has non-real eigenvalues, what's the proper definition of L to the alpha?
Oh, we just take the main the first we choose the determination of the power L to the alpha that gives us an M matrix, and there's a unique one. This requires proof, of course. So this fact was proved for the pth root of a singular M matrix already, at least for a non-singular M matrix. This was proved by Guo, and in our paper we extend this to our situation of a singular M matrix. But another way to do that, we can use the binomial series and use that to define the alpha power of the Laplacian, and we can prove that the series converges, and it converges to, in fact, a singular M matrix. So one can use the definition based on the Jordan form, and then make sure to choose the primary branch of the alpha root, the one that will give us an M matrix. So complex eigenvalues are not a problem. They can be handled just as easy.
Okay. Yeah, let's just carry on.
Okay.
Thank you.
Sure. Okay, so let's talk a little bit about properties of the fractional dynamics. So as I already pointed out, the fractional Laplacian is going to be, in general, a dense matrix. This can be seen, for instance, by looking at the binomial series expansion. If we have an irreducible sparse matrix and we take a power series in that matrix, the result typically will be, in general, a dense matrix. However, we can do something more than that. We can actually quantify the size of the entries, assuming that the matrix L is sparse. And for simplicity, you can think of the case where L is a banded matrix, even tridiagonal if you like. But everything that I'm going to say can be generalized to more general sparsity patterns. So an observation to be made here is that the alpha power of x, and therefore also this exponential, are not analytic functions. They're only Holder continuous function. And so we are going to be able to prove an estimate or bound of the entries of either one of these functions of this form. We're going to have a constant divided by the distance between the node I and node j, using the geodetic distance of node I from node j in the graph, with a limitation that we're looking at a distance of at least 2, but this is not so important. And then everything is raised to the alpha power. I should say that here my focus is going to be on the case of undirected graphs, where L is symmetric. In this case, the geodetic distance is indeed a distance. The geodetic distance is just the length of the shortest path between two nodes. It's the true distance on undirected path because it's a symmetric function, of course, of I and j. On directed graphs, we can still define the distance between two nodes, but it may not be a distance in this. It is not in general a distance in the standard sense of the word. So what we have, in other words, is that for alpha Holder continuous function, we have a power law decay in functions of sparse matrix L with exponent alpha. So the decay can be quite slow, right? If you take alpha equal 1/2, so we look at the square root of the Laplacian, this says that the entries decay away from the diagonal, say, if L is tridiagonal, for instance, like the square root of the distance. This is in contrast with analytic functions of sparse matrices, which are known to exhibit much faster decay. For instance, exponential decay, and in fact, for entire functions that are analytic everywhere, even super exponential decay. And this was established a long time ago in a paper I wrote with Gingol. So for instance, in this paper, it follows that if a matrix is, say, banded, and we look at the matrix exponential, which is an entire function, then for any t fixed greater than 0, the entries of e to the minus t hal, the so-called heat kernel, exhibit an off-diagonal decay, which is given by a normal distribution, a Gaussian. So the decay is very, very fast away from the main diagonal. And this explains in what sense the classical diffusion dynamics on a network is localized. If I start at a point in the graph and I apply this matrix exponential and I look at the solution after a time t fixed, the solution will be normally distributed. Of course, the width of this Gaussian increases with time, but for small times or not too large times, the diffusion remains local, and the width of the Gaussian, of course, grows in time, but in a gradual manner. In contrast, if we look at functions that are only Holder continuous, the decay will be algebraic, and so we have a less localized dynamics. So here I express this power law decay separately for the two matrix function, alpha power of L. Again, we're in the undirected case. So this is true for any Laplacian, but our focus in particular will be on sparse Laplacians. So there is a constant term here, constant in the sense that it doesn't really depend on the distance on the graph. It involves a spectral radius of L and 2 to the power alpha. And then we have the decay term. The decay again is like a power law. For the exponential of this minus TL to the alpha, I don't need the absolute value here because this is an essentially positive matrix, so its exponential is always a non-negative matrix and strictly positive in the irreducible case. We have the same bound, but now we get t, the time variable that multiplies there in front. So we see a much less localized behavior compared to the standard non-fractional case. We can also use these estimates to bound the entries of the stochastic matrix that defines the random walk associated to the normalized fractional Laplacian. And so the entries of P alpha now, of course, are real numbers between 0 and 1 because it's a stochastic matrix. So the bound is, again, we have some constant here, and again, the same type of power law decay. And this constant C here is given by 1 plus pi squared over 2. This bound should be read in the sense that the right-hand side should be taken to be the smallest between 1 and whatever we see on the right-hand side. For small graphs and short distances, the right-hand side of this inequality is greater than 1. So the inequality doesn't tell us anything. But if you go sufficiently far in the graph so that this number becomes small, eventually the estimate will become less than 1. And the bound will be informative. How do we get these estimates? It's straightforward, basically fairly straightforward application of classical results in approximation theory combined with the spectral theorem. So in the paper with Golub from more than 20 years ago, we used Bernstein's theorem on the polynomial approximation of analytic functions using the infinity norm. Here, the functions are no longer analytic. They're much less regular. In fact, they're only Hölder continuous. And so instead, we have to turn to another classical theorem in approximation theory for real functions called Jackson's theorem. So Jackson's theorem says that if we have a function that has modulus of continuity omega, and remember, modulus of continuity is a function that measures how continuous a function is, quantifies how continuous a function is in a way. Then the best approximation error using polynomials of degree less than or equal than a given integer n is given by c times omega evaluated at b minus a, length of the interval, divided by 2n, where c is this constant 1 plus pi squared over 2, which is the origin of that constant on the previous slide. In particular, we will see what this modulus of continuity is in the case of Hölder continuous functions. So how do we apply this to matrix functions? Well, we use, again, essentially the spectral theorem. But the first thing to observe is that if we define if the distance between two nodes is given by m plus 1, where m is integer, then the ijth entry of L to the power k, L is the Laplacian, is going to be 0. This is because of the interpretation of the powers of a matrix in terms of basically walks between nodes. So this implies that for any polynomial of degree less than or equal than m, we can write the difference of f, the ij entry of f of L minus the ij entry of the polynomial Pm evaluated at L. So this is the same because this is 0. And now we use the spectral theorem to bound that. Well, this is true for any vector, in fact, or matrix. So the 2 norm of that difference is going to be greater or equal than the difference of those 2 elements. And now we use the spectral theorem. Since the Laplacian is symmetric, we have that for any polynomial Q, we can bound the 2 norm of the difference between f of L and q of L by the difference of the scalar functions f of L minus q of L, infinity norm taken on the interval containing the spectrum of L. the spectrum of L is contained in the interval 0, spectral radius of L. So now we can apply Jackson's theorem and conclude that the ij entry of f of L is going to be bounded by this quantity here. To conclude the proof, we observe that the fractional power of x are Hölder continuous and with modulus of continuity equal to the function itself, x to the alpha. And so plugging that in, our formula above, we obtain the bound for the powers of L to the alpha. So this means that the bound, the entries of L to the alpha are bounded in a way that decays like a power law with exponent minus alpha, say away from the main diagonal, for instance. And with a little trick, we can extend the proof also. We can also prove the same similar bound for e to the minus tx alpha. So let's look at an example to see if the bounds capture the actual behavior of the entries of the fractional Laplacian. Here we look at a graph which consists of the road network of the city of Washington, D.C. It's a graph with 9,522 nodes. It's actually a part of it, I guess. So this is the graph. You can't see the nodes and the edges very well because it's quite large and the resolution is not that great. We pick one node, which corresponds more or less to the geographic center of DC, and then we look at the decay away from that node. So the distance of all the nodes in the graph from that particular node, using the entries of L alpha as weights. And here is the bound. So if you compare the two, you can see, of course, the bound overestimates a little bit. The color code is that nearby nodes in this metric are given by lighter colors, and darker colors, I believe. No, sorry, these are sorry, these are going negative. Yes. Anyway, you can see that the decay is captured, although the orders of magnitude are different, to say the least. And this is due to the constant in front. But definitely the entries do obey a power law decay. Now, we would like to extend this to the directed case, but this is unfortunately very, very difficult. We can see it numerically, but proving it is another story. The difficulty comes from the fact that the Laplacian of a directed graph is almost invariably a non-normal matrix. So now, in order to extend the bounds, we need to make use of the field of values or some other spectral set. So the field of value of a matrix, L in particular, is defined here as the set here. And we need the matrix function, the scalar function x to the alpha, to be defined on the field of values for us to be able to derive useful bounds on the matrix function. And the problem is that the origin, so 0, which is an eigenvalue of the Laplacian, always falls inside the field of values. Basically, it's very rare that it's on the boundary. Almost always it will fall inside. And so, in particular, the field of value will contain a segment of the negative real axis, and therefore the fractional powers will not be defined on this set. This is a well-known difficulty when dealing with non-normal matrices. In spite of this, we do observe the decay numerically, and in fact, we can even prove it analytically in some simple cases. So I probably need to speed up, but let me tell you one case where we can prove it is the simple directed path graph. Here we have simply a particle that moves from one node to the next in one direction on the line, and there are n nodes. And then once it reaches the last node, it stops. So it's an absorbing type of process. And here we can actually compute analytically the entries of the transition matrix. It leads to expressions involving the gamma function. And asymptotically, for large distances, we can obtain the estimate given here, which you can see depends algebraically as a power law on the distance. We can also do this for the cycle graph. Now, when we get to the last node, we circle back to the original node. So this is a periodic type of process. And again, using the gamma function and some analysis, we can show that the transition probabilities decay like a power law. So an application of this is network exploration. So random walks are used to explore networks. You're all probably familiar with the PageRank algorithm, which is a way to explore the web graph and determine the most important nodes. Local random walks, of course, tend to converge more slowly, as one would expect, than a non-local random walk that allows me to jump all over the place, at least with some probability. Maybe not very often, but at least occasionally. So we verified this. This was observed by Riascos and Mateos for undirected graphs. We wanted to see if this also holds for directed networks. So if you look at the probability, the conditional probability of being at a node I at time t, and we started from node I0 at time t equals 0, then we can express the, we look at the average return probability. So we sum all these conditional probabilities and divide by the number of nodes. This is equivalent to taking the trace of this matrix exponential and divide it by n. Okay, so this is a real quantity. And we hope that this quantity, so the average return probability should be higher for a non-local dynamics. So we looked at the three directed graphs. One is the Roget network. These are often used in testing algorithms for directed graphs. One is Wikivote and the other is Nutella. So these three graphs have different characteristics. It turns out that we should focus on this number here, which is the largest, the size of the smallest non-zero eigenvalue, the absolute value of lambda 2. It is smallest for this network Roget. It is quite a bit larger for the network Wikivote and still larger for Nutella. The rate of convergence to steady state of the random walk is faster the larger is these eigenvalue, the lambda 2 eigenvalue. And this is true whether you use the classical or fractional dynamics. This scale is logarithmic, so we have time on the x-axis and the average return probability on the vertical axis. So notice again, these are logarithmic scales. For this graph, where the smallest eigenvalue, the smallest non-zero eigenvalue is close to 0, the spectral gap is small. You can see that the classical dynamics that corresponds to alpha equal 1 takes quite a bit longer to reach the steady state. The steady state is given by 1 over n. The other, the fractional dynamics for different values of alpha converge quite a bit faster to steady state. So we can say that the exploration of the graph is much more efficient. Remember, again, this is logarithmic scale here. So much more efficient for this fractional dynamics with alpha equals 0.25 than with the other values of alpha. Again, this is a measure of how fast we sample the network, if you like. On the other hand, for this network, which has a larger spectral gap, the non-fractional, the classical dynamics converges faster. And therefore, the gain in using fractional diffusion is smaller. There's still some gain, but it's small. In this one, which has a fairly large spectral gap, all methods are equivalent. So they give the same speed of exploration. So it also, we looked at the diameter of the networks here. 14, 9, 19, this is the diameter is the distance, the maximum distance between two nodes in the graph. But it doesn't seem to play a role. The spectral gaps seem to be more important. Okay, we also proved the property called superdiffusivity or anomalous diffusion using the graph Laplacian. I realized that I'm running out of time, so I think I will skip this part, but I'd be happy to take questions on it. This is, as far as we know, the first rigorous proof of superdiffusion behavior, which means that the mean square displacement, which is this quantity here, grows superlinearly in time for network dynamics. We also studied the case of directed graphs. Well, maybe before I enter the last part, which is about Krylov methods to compute these matrix functions, I should ask if there are any more questions at this point.
Yeah, there are a few. I'm just asking one and then let you go on,
Okay.
which probably relates to the part that you just talked about and which your former colleague, Lars Rusotto, already answered partly, but I'll just ask it anyway. So Bibas Adhikari, hopefully I pronounce this right, asked why is the value alpha taken from 0 to 1?
Okay, we're looking at fractional operators, right? So the question could be, is ambiguous. And so in the case of continuous Laplacian, it's known that alpha must vary between 1/2 and 1. Otherwise, the moments of the distributions are not defined, they're not finite. But in the matrix case, there's no such limitation. We can take any alpha between 0 and 1. So a commonly used value is alpha equal 1/2, the square root. In reality, well, I mean, we could define alpha greater than 1, but it is in mathematical physics, fractional diffusion is really corresponds to values of alpha between 1/2 and 1 for physical reasons. So I don't know if this answers the question, but of course one can do whatever one wants, but you can even take values of alpha greater than 1, but then we can factor out L in a sense. So it's important to focus on the fractional case, because we can also factor out integer powers of L. Those are less problematic to study.
Okay, thank you.
All right. So let's talk a little bit about computation. This won't take very long. So of course we cannot compute the whole matrix function for large cases because it's a dense matrix. But as we saw in the dynamics processes, the study of dynamics, we really want to study the evolution of the initial condition over time, typically, or do a random walk computation like a power method. So we really need to compute the action of a matrix function on a vector, which is a pretty classical problem when dealing with matrix functions for large sparse matrices. So there are many methods to do this. One can use quadrature rules, for instance. Here we will talk about Krylov methods. Most of you are familiar with Krylov methods. Of course, they're based on matrix vector products, for instance, to construct a low-dimensional search space, constructed using the matrix and the vector. Then the matrix is projected using an orthonormal basis for the subspace on the subspace. One evaluates the matrix function on the projected matrix, which is small, and then lifts the result back to the original space, Rn, by this formula, very, very briefly. Of course, we have to compute this matrix function inside, but that's a small matrix, so typically we can use either diagonalization or more generally the Schur form, Schur-Parlet type methods. So there are various types of methods, polynomial Krylov methods, shift-and-invert type Krylov methods, and rational Krylov methods, which are briefly listed here. And of course, the rational Krylov method include special cases, the previous two for a special case of the functions that appear here. So the function q that appears in the rational Krylov method it needs to be defined. It's going to be a polynomial, and this number c1, ck minus 1, the poles have to be specified. So there are some error bounds, going back, for instance, to Stefan Gittel's thesis, that can be used for rational Krylov methods if f is analytic on the field of value. So in particular, in the case where f is the exponential, for instance, and the matrix L is for any matrix, in fact, and then we can use bounds of this kind. I used the value of Palencia and Cruzet here for the constant C, for those of you who are familiar with this. The problem is that the graph Laplacian is singular, our function is not analytic, so we cannot use general error bounds of this form. Of course, we can also always desingularize the Laplacian. So let me assume again the graph is strongly connected, so there's only the zero eigenvalue with multiplicity 1. If we have left and right null vectors of L, then we can modify L by adding this rank 1 matrix, XY transpose. This is always going to be non-singular. And then we can compute f of L, or its action on a vector, using this simple identity. In the case of undirected graphs, both x and y are going to be the vector of all ones. In the directed case, x is going to be the vector of all ones, and L is going to be a solution, y is going to be a solution of this homogeneous system. So this has to be computed in order to perform the rank 1 modification. Unfortunately, this doesn't help a whole lot because when L is non-symmetric, the field of values of the perturbed matrix, or the modified matrix, still will contain, most likely than not, more likely than not, a portion of the negative real axis from which the matrix function is not going to be defined. The function x to the alpha is not going to be defined. But in the symmetric case, this works. We also found numerically that removing the singularity from L actually helps getting higher attainable accuracy and better convergence in the Krylov methods. And this may be already known, but we certainly observed this. So let me show you, to finish, some experiments. We focus on the exponential of minus t L to the alpha, with different values of alpha and t. We use the polynomial Krylov method, the shift-and-invert Krylov method, both with and without this rank 1 modification of the Laplacian. For the choice of poles, we either use the repeated pole, so we use the repeated pole, C equal minus delta, where delta is either the square root of lambda 2 times lambda n, or delta is given by this power of t, the time variable. And this second choice is proposed by Moret and Novati in a recent paper in Math Comp, and it has the advantage, of course, of not requiring knowledge of the eigenvalues. And we performed some experiments on the largest connected component of several graphs of moderate size, about 1,000 nodes. So here are some of the results. So here we look at the first graph. This is a power grid network from Boeing Computer Services. It's a power grid, so it's a network indeed. We started with a random probability vector, and then we compute for alpha equals 0.5, this matrix exponential times this vector, for 2 times t equal 1 and t equal 10. So the first thing to see is that the polynomial approximation is very bad, with or without the singularization. Removing the singularity helps, but it's still very slow convergence. And this is what we expect, because we know that polynomial approximation converges very slowly when we approximate Holder continuous functions. This is Jackson's theorem, essentially. In contrast, the various rational method, the shift-and-invert method in particular, perform very well, in particular with the choice given by the square root of lambda 2 times lambda n. The convergence is very fast. Whether we remove the singularity or not, it doesn't make a lot of difference. If we use the choice suggested by Moret and Novati, we have somewhat in between convergence, with, better than polynomial, certainly not quite as good as shift and invert with the other choice of the pole. And there is some improvement when we remove the singularity. This is the same problem, but now we look at time t equal 10, again, square root of L. Again, this is a symmetric matrix, I should say, it's undirected. Polynomial approximation, very slow. All the rational approximation, with and without the rank 1 modification, converge fast. Now let's move to a directed graph, so non-symmetric problem, the Roget network. Now we use t equals 0.5 and t equals 50, and alpha again is 0.5. Again, we see that the polynomial methods are not as bad as earlier, perhaps, at least for small time. They do converge. There's some little bit better with the Moret-Novati strategy for the shift and invert method. the choice of pole given by the square root of lambda 2 times lambda n gives the fastest convergence. Whether we remove the singularity or not doesn't make much difference. When we go to large times, interestingly, here removing the singularity of the Laplacian is essential. We have a very sudden growth at the beginning. Probably some rounding errors get into the null space and get amplified before we start seeing the convergence. Removing the singularity removes this jump, but we still have very slow convergence. And you can see that all the rational methods do much better, and in particular the ones with the choice suggested by Moret and Novati, in this case, converge very, very fast. And now another example, the wiki network, also directed, same fixed time t, 2 seconds after, say, time 2, and 2 values of alpha, 0.25 and 0.75. Again, you can see that the rational methods perform quite well in both cases, and the polynomial methods converge quite slowly. Same thing now, still wiki vote, now t changes and alpha is fixed. Once again, we see the very good convergence behavior of the rational methods. For small t here, it's the choice lambda 2 times lambda n, square root of that gives the best convergence. For larger t, the Moret-Novati choice gives the best convergence. So it really depends on t. The choice of poles seems to depend on t. Let me conclude. So fractional diffusion is a powerful modeling tool for applications ranging from epidemiology, network exploration. In the paper, we discussed consensus dynamics. I didn't have time to talk about it here. We have established power law decay behavior and superdiffusivity for the fractional Laplacian dynamics on undirected graphs, provided some evidence for it on directed ones. We discussed rational Krylov methods for computing these quantities. It seems that helps to remove the singularity of the Laplacian explicitly whenever possible. Unfortunately, there's a lack of theoretical tools for analyzing the convergence behavior and also the decay behavior in the case of non-normal matrices, but this is a well-known problem. And with that, I thank you for your attention.
Thank you very much, Michele. And I'm really impressed by the particularly timely application you talked about. You mentioned non-local modeling phenomena of disease that we are seeing every single day. So I'm really impressed. So, but let me leave to Melina for the question and answer session.
Okay, so in the interest of time, we probably choose some questions, but I have one more before I head to the YouTube questions. So Phil Knight asked during the talk, if your graph is undirected, does it matter that your normalized Laplacian is non-symmetric?
We just did what Fan Chung does in her papers. I mean, there are several ways one can normalize the Laplacian. This is the one that makes sense when using the outlet. Yeah, I mean, it probably doesn't matter a lot because in the non-symmetric, in the symmetric case, it probably shouldn't matter. You would just define the diffusion process, I suppose, slightly differently.
Okay.
Not a big difference, I would say, no.
Yeah. Okay. So one more question by Lucia Young is, does the rank 1 update correction work for all functions, f, or just polynomial and exponentials?
L to the alpha is not a polynomial, but I could answer by saying that every matrix function is a polynomial, of course, in the matrix. But no, it's a general relation.
Okay, I think I'll head over to Stefan for some more questions on YouTube.
Yes, hello. YouTube speaking here. We had a good audience of more than 100 people. There was only one question so far by Martin Stoll. He asks whether the dynamics modeled by a Laplacian with a transport term on an undirected graph can be somehow compared to the dynamics via Laplacian on a directed network. So can somehow the transport term be incorporated?
This is one of the things that I skipped when discussing diffusion, super diffusion. So we looked at the undirected path graph, and for the purpose of analysis, it helps to look at the infinite case. And we were able to find, to prove in this case, the dynamic is super diffusive. What's interesting is even in the standard diffusion, the non-fractional one is super diffusive in this case. And so this seemed to be a little surprising. Of course, the diffusion here is one-sided because the particle can only move in one direction. So when, if you look at the third bullet here, our explanation of this phenomenon was that the Laplacian of this simple path graph, directed path graph, is not really a second order diffusion operator, but it's an advection operator. It is really transport operator. So this is a bit of an extreme example in which every node, because in the directed path graph, every node is a strongly connected component by definition. In real networks, we would have a mixture, perhaps, of advection and diffusion. So it is possible that the out degree Laplacian is precisely this mixture of advection and diffusion when working on a directed graph. So in the extreme case where the directed graph becomes undirected, every connection has its opposite in the graph, this becomes pure diffusion. In the other extreme, where all directions are one directional, the motion, the flow is one directional, we have pure transport. And in more general graphs, we have a mixture of the two. I have to say, this is something we're trying to figure out for a long time now, thinking about how to interpret this operator, this non-symmetric Laplacian, and this is the best we could do.
Mm-hmm. And actually a related question by Gerard Moron, how do you actually choose alpha in real life problems?
Use machine learning.
Okay, with this I hand back. Thank you.
Okay, it's me again. There were some more questions in the meantime. There's one which I'd like to ask by Bernd Beckermann, I assume, only put down the first name. Can you tell more about the cut in the complex plane to make x to the alpha single valued?
No, I mean, we don't have to, right? Because it's maybe some misunderstanding here. So we don't do that, and maybe we should. I don't know. But the function L to the alpha is defined on the non-symmetric Laplacian because 0 is a semi-simple eigenvalue. So we can use the Jordan form, for instance, and to verify that it's defined. And if you look at the principal determination, it can be proved it's a matrix, which is what we need. When we want to look at larger sets, like the field of values, to study the decay behavior or to get bounds with the convergence of Krylov methods, we're stuck because we find ourselves with a piece of the negative real axis inside the field of values. And you know this is a problem even for defining Krylov methods, which usually assume that the function f is defined for the field of values of all the Hessenberg matrices generated by the Arnoldi process. And we can't do that. We can say that. It turns out it works in practice, but we don't know how to do that. Now, if there's a way to do that, considering cuts on the complex plane, I'd like to know more.
Okay, thank you. Thank you very much for answering the questions. Since we are past 5 o'clock, I'm heading back to Valeria.
Okay, thank you very much. So I would like to thank Michele once again for this very inspiring talk. And I would like also to thank the audience for joining us today and for asking several questions. And I hope that you all join us again on next Wednesday when we'll have Volker Merman from TU Berlin. So have a good rest of the day. Bye-bye.
Thank you. Bye-bye.